So what are we doing today?
Well, what we're doing in math is two-way tables, but it's pretty straightforward. So there is something, what we missed last week was computations and permutations.
Okay, let's look at those. Got some
Okay.
problems? First of all, before we do anything, let's define the general formula.
Yeah. Okay.
What's that equal to?
N over R.
N factorial.
Oh, yeah, N factorial, sorry.
Over N
Over
minus
N.
R factorial.
Okay.
For example, 3 pick 2 would be 3 factorial over 1 factorial, which is 6.
Okay.
Alright. Now let's talk about combinations, because they're a little different. N choose R is equal, starts out exactly the same, but then there's one more term, and it's R factorial. And kind of the way I remember that is, I know it starts out the same, but it ends up with 2 N's and 2 R's in it. Okay? So as long as I know it has 2 N's and 2 R's, well, by the time I get to this point here, there's only one term that could be left, and that's R factorial. That's the only way I could have 2 N's and 2 R's. An example of this would be 8 choose 6 equals 8 factorial over 2 factorial times 6 factorial. Now, let's talk about that number. I know you can do this on a calculator, but let's do it without a calculator.
Okay.
What is 8 factorial?
8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Or being, I guess it is times 1, but I don't know if it matters.
Doesn't matter. We could leave the 1 off. 6 factorial. Times 2 factorial. Well, notice how this works. The 6 factorial cancels out that 6. So what I really end up with is 8 times 7 divided by 2.
And that's the answer if I had done it the whole way, or?
That's definitely the answer to my problem. In other words, 8 choose 6 is 8.
So you can cancel out the remainders of it.
Yeah, that's why I wanted to show you that, because I know, what kind of calculator do you have, Dominic?
Let me go get it, and also my iPad, so maybe I can find a problem or two to give you.
Okay.
I have a TI-30X 2S.
Okay, it might, I'm not familiar with that, but it wouldn't surprise me if that did not let you do factorial. Does it let you do factorial?
Well, I don't see an exclamation point, so I'm not sure.
So probably not, which means you're going to have to do them all this way. Now, not that that's hard. Let's take another one. Tell me what this is.
That is just, I guess, 49 over 1? Or?
Well, let's just remember that it's only the 7 times 6 that's left over.
Yeah. I mean, not 49. Oh my gosh.
Okay, so that's
42.
the answer, 42.
Yeah, 42.
Right.
Not 49.
In other words, this is always going to be 7 times 6 because the rest of it cancels with the denominator.
Uh-huh.
That's the way you look at it. Doesn't matter whether it's a combination or a permutation. Now, the difference between permutations and combinations is permutation order matters. Combination order does not matter.
Uh-huh. Yeah, I remember that a little bit.
Do you play cards at all, Dominic?
Yeah.
If you have an ace of hearts, 9 of hearts, 6 of hearts, 3 of hearts, and 2 of hearts, you have a flush, an 8-prime flush. But it doesn't matter if they come in this order. If you get the 9 of hearts first, and then the 6, then the ace, and then the 2, and then the 3, you have the same hand.
Uh-huh.
There is a perfect example of where order does not matter. In other words, if you want to figure out the odds of you getting this ace-high flush, then it would be a combination problem, not a permutation problem. All right. What kind of problems do you have for me?
Let me check. There's also two-way tables, but those are pretty easy.
What do you call those? You said that twice, and I didn't hear you either time.
Two-way tables?
Meaning what?
Like, it's like a table, like 2 by 2, I guess. I mean,
Like X, Y at the top?
it's like, no, it's like cut into, like, a bunch, like, it's like grouping up stuff and, like, seeing the totals of them based on totals. It's like taking a total, it's like a survey, and it breaks up the, like, the different party voters depending on how old they are, or...
Okay, I understand now. It's where you've got 4 different options.
Yeah.
In other words, let's say you have people that eat spinach and other people that eat lettuce.
Mm-hmm.
And you have men that eat spinach and men that eat lettuce, and you also have women that eat spinach and women that eat lettuce. That would be a two-way table.
Mm-hmm.
Because you have 4 options. Now, if you need help on those, I'm happy to work with you on those, but I'm going to let you direct totally. You tell me what you want to work on.
Okay. Let me see. I don't really know.
Well, let's go back to combinations and permutations. Do you have any problems with those?
I don't, and I get them pretty good from what I can tell.
Hold on, let me open my book, and I'll bring some.
Okay. Okay.
Because these are the basis of a lot of things, actually. Combinations and permutations, as surprising as that is.
What is it?
He said it's the basis of a lot of higher math.
And it's surprising I'm learning it, or just...
No, it's surprising that it is the basis of higher math. Let's say there's 12 skiers in a competition. How many different ways can the skiers finish the competition, assuming there are no ties? So we have 12 competitors. How many different ways can they finish?
12 competitors, how many different ways can they finish the race? Like in what order?
Uh-huh.
So when order matters, it's a permutation, right?
Well, it is, but oddly enough, I'm not sure that this really uses the permutation formula.
Oh,
The
sure.
way to look at this is how many different skiers can finish first?
12. Oh, wait, is it just 12 times 12?
It's 12 times 11.
11.
That's
Because
the
you can repeat.
number of ways, that's the number of people that can finish second once somebody else has finished first.
Mm-hmm.
10 times 9, in other words, 12 factorial.
Oh,
That's how many different ways the skiers can finish.
what is 12 factorial?
Well, I don't know. I don't care. That's a number, okay? You can always get that out of your calculator. Well, most calculators you could.
Wait, really? Wait, what's the question again?
How many different ways can 12 competitors finish a ski race?
The answer, wait, really?
Hmm?
This sounds weird, because 12 factorial, I looked it up, and it says it's like 47 million, or like 479 million.
79,001,600. That's the number of different ways that 12 skiers can finish a race.
Wow.
And that's a permutation problem because order matters. In other words, we're talking about one skier finishing first, and then one of the remaining 11 finishing second, one of the remaining 10 finishing third, and so forth and so on. It's still a permutation problem, even though we don't use that formula, but we'll get to that. Now, the second question would be, how many different ways can 3 of the skiers finish first, second, and third to win gold, silver, and bronze?
Mm-hmm.
Well, that is 12 skiers pick 3 different ways. Well, that's 12 factorial divided by 9 factorial. What's that equal? What's that equal to? Cancel the denominator. That's
Yeah,
your first
so
step.
I'm going to give it my calculator, I guess.
No, you don't need to do it with a calculator. That's the answer right there.
Oh, you don't even have to solve it?
Well, I don't care. I'm not concerned with the answer. What I care about is the setup.
Okay, well, yeah, I get that. I get that you just made it.
But it's also easily done without a calculator. In other words, you don't need to put 12 factorial divided by 9 factorial.
Yeah.
It's important to be able to go from that step to that step. Knowing that the 9 factorial cancels out with everything below 10. So what you're left with is 12 times 11 times 10, whatever that number is. That's 1320. But like I said, I don't care what it is. It's a permutation problem, though, because this is choosing, 12 skiers picking 3. We don't care which 3. 3 skiers are going to finish first, second, and third. We're just trying to figure out the number of different ways they can finish first, second, and third. And it turns out that there's 1,320. And this is a classic permutation problem.
Okay.
Now, let's talk about some other probability and combination problems.
Okay.
York license plates have 3 numbers and 3 letters. How many different license plates can you have without a repeat of numbers or letters? So how many different numbers can you have there?
You can have 3 different numbers.
10. 1 through
Wait.
1 through 9 plus 0. So I can have 10 different numbers there.
Oh, just in that one digit?
Right.
Oh, okay.
In other words, I'm trying to figure out how many different unique license plates I can make.
Uh-huh.
Okay? And that's a critical problem. If I've got 100 million people in the state and I can only make 10 million license plates, then this system isn't going to work, right? I got to have a unique license plate for every driver. So this is actually a practical problem. And what I've said is that I can not repeat numbers and I cannot repeat letters. So how many possible numbers can go there?
9.
How about there?
8.
How about letters? How many can go there?
How many letters are in the alphabet again?
26.
Okay, and then 25.
There? 25.
25, and then 24.
Whatever that number is, and it turns out that it's not as big as you might think, 11 million. So if I've got more than 11 million people in my state, I got problems. So let's go back and not worry about whether we repeat numbers or letters. So now how many letters or how many numbers can go there, there, there? How many letters, letters, and letters?
10, 10, 10, 26, 26, 26.
And just doing that one change ups the possibilities to 17 million. And if you think about it, there's no reason why you wouldn't want to repeat numbers. In other words, as long as you end up with a unique number for every driver, you don't want 2 drivers to have the same license plate, right?
No.
So, as long as you've got 3 numbers and 3 letters, you can do 17.5 million unique license plates. That might not get you by California, though. I don't know how many cars they have, but they've got like 30 million people out there. So they're close. Okay? So these kind of questions are not immaterial. In fact, let's talk about a phone number. How many different 7-digit numbers can you get? In other words, when they originally came out with phones, they had to make sure that their phone numbers covered everybody that lived in the area. So, not counting the area code. In other words, if you're talking about just in one area code, how many different numbers can you get?
Well, it'd be 10, 9, 8,
Actually,
7.
the second number can be the same. There's no reason there's no reason to not be able to use 2 twice.
Okay, so 10, 10, 10, 10, 10, 10, 10, 9? It can just go 10 all the way?
Nothing prevents you from having this phone number.
Oh, that's true. Yeah.
In fact, a lot of cab companies have that phone number. So what we have is 10 to the 7th power, which is 10 million, which is surprisingly small.
Uh-huh.
I mean, that means the maximum phone numbers you can have per area code is 10 million. And that's if you use all combinations of the first three numbers. And most states do not. In other words, they don't use 411, right?
Mm-hmm.
They don't use 911. So
Uh-huh.
they don't use all 10 million of these combinations. But you can see that as soon as you get more than 10 million, you're going to have to come up with a different area code. In other words, that happened to Colorado about 15 years ago. They ran out of phone numbers, so they had to introduce a 720 area code because they had used up the number of phone numbers that they could make from just 7 digits. But of course, with 10 digits, that's a lot more. Now it's 10 to the 10th instead of 10 to the 7th, and 10 to the 10th is,
A lot more.
well, it's a 1 with 10 zeros behind it. So that's
Uh-huh.
10 trillion. So as long as you have an area code, you can use 10 trillion numbers. Excuse me, that's
Oh.
not 10 trillion, that's 10 billion.
Uh-huh. Okay.
Okay? In other words, that's 1 million, that's 1 billion, that's 10 billion. 10 billion is still a lot. There's only 7 billion people that live on the planet.
Yeah, I was about to look that up.
So, yeah. If you want an interesting fact, though, give me a guess as to what that's equal to.
50 factorial.
Uh-huh.
Um, sheesh. Wow. A lot.
Take a guess at what that exponent is.
What, the x?
Well, it's 3 times 10 to some power is what the answer.
Oh. Oh, yeah, okay. Equals 3 times 10 to the 5th, the 64th?
64. Yes.
Okay.
That's more molecules that exist in the entire universe, the entire observable universe.
Wow.
So that is a gigantic number. Who knew?
Doesn't look like it at first.
It doesn't. Even if you think about it, 50 times 49 times 48, you would never imagine that you would get up to this size number.
Mm-hmm.
And the fact that that's more molecules than are in the entire universe is striking. That means it's more than the number of grains of sand on planet Earth, more than about 100 million times that. And
Wow.
that's just 50 factorial. So factorial growth is huge. In fact, if I said to you, which grows faster, exponential or factorial growth?
Factorial.
Yeah, by a lot.
Since exponential just grows by like the same number times itself, right?
Exponential grows like that. So exponential grows very, very fast.
Yeah.
But factorial is faster. But
Uh-huh.
not on low numbers. In other words, if I were to look at 3 factorial and compare it to 2 to the third, 3 factorial is 6, 2 to the third is 8. So with low numbers, exponential actually grows a little faster.
Uh-huh.
But as soon as you get up, in other words, if you had 50 factorial divided by 2 to the 50th power, despite the fact that that's a big number, 2 to the 50th power, it's nowhere near 50 factorial.
Mm-hmm.
So when you get to calculus and they start talking about limits, one of the things they teach you is that factorial growth is faster than exponential growth. And in fact, when they talk about large numbers and high growth rates. Those are the two that they tend to use. Factorial growth is about as fast as it gets, even though everybody uses the word exponential to mean as fast as it gets. In other words, if I've got a beanstalk in my backyard and it's growing and I want to say it's really growing fast, it's like exponential growth. It's going to be 4 feet high today and 9 feet high tomorrow and 16 feet high the next day. But in reality, if I really wanted to exaggerate, I would say it's factorial growth.
Mm-hmm.
But nobody does that because nobody realizes that, other than mathematicians, but nobody realizes that factorial growth is a lot faster than exponential growth.
Okay. Well, I guess that's it for today, since I don't know what else we're going to talk about.
Yeah, that's fine. We covered a couple of fundamental combination and permutation problems, and those are key. So, yeah, that's fine. Dominic, I will let you go, and I'll talk to you next Tuesday.
Okay.
All right, bye-bye.
Have a good day.